Hello there and welcome back. We are starting our next lesson on interference and diffraction. And so hopefully part of what we're going to talk about right now is going to be a little bit of a review of some things you already know about waves, but then we're going to extend that into how it plays out with optics and how light might interfere or diffract and so on. So you might recall that whenever two waves occupy the same space at the same time, they will interfere with each other. And essentially they follow something called the principle of superposition, which just says that the total amplitude of a wave at any given point is equal to the sum of the individual waves. The sum of the individual waves. So what does that mean? Well, you can see here over on this graphic over here that sometimes crests line up with crests and they make a really big crest, and sometimes troughs line up with troughs and they make a really big trough. So when the crests of the waves line up, we say that they're in phase, and we observe something called constructive interference. Now that word interference might be a little bit off-putting, but they can interfere in a way that they add up and become bigger. Interference just really means interaction in this case. And so if I have a crest line up with a trough, and we say those waves are perfectly out of phase, and we get destructive interference. Destructive interference. Okay, so this leads us to something called standing waves. Now you may have seen this like in a slinky or a spring, or if you take a string and you kind of wave it back and forth, you can make these waves. You can see down at the bottom here, this is my overall waveform. So if I've got a slinky and I kind of wiggle it back and forth, I might set up this standing wave. And it's a standing wave because it doesn't look like it's going anywhere. I see crests and troughs kind of occurring in the same spot. And then in between those places, I see kind of not much happening at all. Now these standing waves are actually caused by interference. They're actually what happens when two waves with the same frequency move in opposition to each other in a string. And so for example, I've got one wave going to the right, the other wave going to the left, and when the crests line up with crests, we make a super crest or a really big crest. And when the troughs line up with troughs, we make a super trough. And when they are out of phase, then they cancel out. So overall what we see here is on this standing wave, we see regions that move a lot and regions that move basically not at all. Where you have complete destructive interference, they have essentially no amplitude. So there is no wave occurring there, and we call those regions nodes. So a region on a standing wave with no amplitude is a node. And then areas of complete constructive interference have a large amplitude, okay, both crests and troughs, so large amplitude. And we call those antinodes. Okay, so any area I've got a large amplitude. So if I have a wave on a spring like I've got here, you can see in this example, if I hit a fixed boundary, then the wave, when it reflects off, is going to invert its amplitude. So it's going to flip, a crest is going to become a trough is going to become a crest, and so on. Now, if that boundary is able to move, is free to move, then it will reflect, but you'll see it's going to stay upright. And so it's going to, let's say, not invert, which is maybe a funny way of saying it. But basically, the wave is going to stay in the exact same phase it was when it hit the barrier. So this happens as well with optics. This happens with light waves. So the parallel to draw with optics is this. When we talk about mechanical waves, when you hit a fixed boundary, you invert, and when you hit a free boundary, you do not. The parallel we draw is in optics. If you go from a medium that has a light optical density into one that's heavier, the wave is going to invert. And if you go from a heavier optical density into one that is lighter, the wave is not going to invert. So you want to keep this in mind. Depending on which medium you're bouncing or reflecting off of is going to tell you whether or not you're going to invert. And a reminder that an inversion, a phase shift of exactly 180 degrees or pi radians, would be exactly half a wave phase shift, like turning a crest into a trough and vice versa. Okay, so let's talk a bit about diffraction. So diffraction is something that we see in all kinds of waves. And so just to start off with, let's think about ocean waves. You can imagine if I have ocean waves kind of rolling onto shore, kind of like this, they're gonna they might hit a barrier. There might be like a breakwater. Now the waves are traveling along this way, so we're looking at like the crests of the waves. Now, you can imagine being in a boat and floating in the water on the other side of this breakwater. And what you would notice is, of course, that the waves do continue through, right? Like the waves that don't hit the breakwater, well, they don't stop. They have no reason to stop. But imagine you were hiding behind that wall. If you were hiding behind that wall, you wouldn't feel no waves at all. You might feel slightly lower, smaller waves. And that's because these waves are going to bend around the barrier like this. Okay, so when these waves strike a barrier, they do continue on, but they're also going to bend around. Now notice that like things like, for example, whatever the wavelength was out here in open water, it doesn't change the wavelength. The wavelength is the same, but it has changed direction. These waves were kind of going this way, and now these waves are kind of going that way. So the bending changes the direction, but not the speed and not the wavelength, and so not the frequency, as long as the medium is the same. So what would happen if we did this experiment but kind of fired these waves at like a small opening? Well, you can imagine these waves kind of coming in like this, traveling along, minding their business, being waves, and then only a small little opening here we would get through. Well, again, the waves in the middle will just kind of continue along, but the rest of the waves are going to bend around in kind of this like semicircular sort of shape, and I'm doing my best to draw concentric semicircles, and this is actually going better than I expected. Amazing. So the waves, when they go through, are going to spread out in all directions, and you can imagine that if this opening was fairly small, it would almost be like a brand new semicircular source of light, almost like a light bulb that you put there and it just shines light out in all directions, as light does. So how do we define diffraction? Well, diffraction is essentially the bending of waves. So the bending of waves around barriers or objects. Okay, so what kinds of things will affect how much diffraction happens? Well, the first thing is think about wave speed. Okay, so the faster the wave is, what's going to happen to the amount that it diffracts? Well, in the picture that I've drawn here above, like it's kind of like perfect diffraction. Like it completely bends around in all directions when it goes through the opening. But I could also have diffraction where the bend is more slight, right? I could have a diffraction that's kind of like, it diffracts a bit, but like not as much, okay? And so what sorts of things might cause this? Well, the first thing is think about wave speed. The faster the waves are traveling when they go through that opening, well, it's going to be harder for them to change direction. So the faster the wave, the less diffraction there is. Okay, a great example of that would be, imagine you're standing outside of like the band room in your school, right? And you're not standing right in front of the door, you're kind of standing kind of to the side. Now the door is open and the band starts playing. When you can't see the band because light that travels from outside of the band room doesn't bend around the corner enough for you to see it. But you can hear the band, and that's because the sound waves are traveling much more slowly. And so when they hit the opening of the door, they do bend around the corner. Now there's other reasons too, the nature of waves and so on, but maybe that's an easy way to remember it. What happens when we change the wavelength? Well, the shorter the wavelength, the less diffraction we see. Now, this is maybe not 100% accurate in terms of why it happens, but the way I visualize this is that if the waves have very short wavelengths, they're like packed one on top of each other, and they're kind of like forcing each other to keep on moving along, right? And so they're going to kind of keep pushing each other forward and allow less bending, let's say. And again, that may not be exactly how it or why it happens, but maybe a way to remember it. And the last thing here is what happens if the opening is smaller? Well, the smaller the opening is, the more diffraction we see. So put these things all together and think about them in terms of optics. Well, we can bend any wave around an opening, but if we want to bend light, which goes very fast and is very short wavelengths, generally speaking, and so we want to diffract that, well, we're going to have to use an opening that's very, very small. And so this is what we see in kind of the famous single slit and double slit experiments. If we have openings that are very, very tiny, we can pass light through it and we can observe their diffraction, their bending. So that actually brings us to Young's kind of famous double slit experiment. Now, just to give context here, like once upon a time, physicists debated quite vigorously whether light was a particle or a wave, right? You might think of some behavior like reflection as being kind of particle-like. It's a little bit like a billiard ball that hits the sidewall, it bounces off at the same angle. That sure looks like it's acting like a particle. And then Young's double slit experiment came along, and it kind of, for a while at least, finished the debate about whether light is a wave or a particle, because when light goes through a double slit, it does something that only waves can do, and that is it creates an interference pattern. And this is something that comes up a lot in physics. We're going to revisit this idea a little bit later. But an interference pattern is very clearly wave-like behavior, and I'll explain why. So imagine we've got a monochromatic planar wave, which is like a laser. And so we mean like a wave that is from a single source, and so it's all these waves are in phase with each other. They all have the same wavelength and frequency, the same color of light, if you will. And they come along and they hit a double slit, okay? Now this double slit opening, you can kind of just look at the top slit for a moment and think about what's going to happen here. Well, light is going to bend when it goes through that opening. And I would recommend grab a colored pen, grab 2 colored pens, and just kind of trace this out just to help you visualize what's going on here. If I just look at the top slit, then I can see that the waves are going to bend around and they're going to form this nice concentric semicircular pattern, which is much easier to trace than draw. And I'm still struggling a little bit, but that's okay. So if I just think about the top slit, the waves are they're gonna emanate out in all directions from that top slit. Now I'm gonna draw in a different color here, and this is really important to point out that these waves are not different colors. They are the same color because they came from the same laser, but it's gonna get confusing if I use the same color. So now picture what's happening from the bottom slit. Well, I'm gonna get these waves bending again, out and around, okay, bending, bending, bending. And if I trace these out, and if I do a halfway decent job, I should start to see some patterns emerging. Okay, so when we carry this forward, and you can just imagine a series of concentric circles that are going to line up in certain ways. Like take a look right down the middle, right here, right down the middle, we can see that I've got a series of red and green lines crossing, and then nothing, and more red and green lines, and nothing, and more red and green lines. Those red and green lines crossing, those are crests crossing, and those blank spots are 2 troughs crossing. So those are areas where I'm going to get constructive interference, and it carries along in a line. And sure enough, what am I going to see here right in the center of a screen? When I project this on a screen, I'm going to see a really bright spot. So if I shone a laser in here, I'm going to see a bright spot show up right there on my screen. And I'm going to see nothing at all beside it, and then another bright spot, and nothing at all, and another bright spot, and so on. And this is going to repeat both sort of up and down the wall, if you will. Okay, so I'm going to get these regular repeating bright, dark, and so on. And why is that? Well, take another line here. You can notice that if I follow this other line here where it says n equals 1, again, I'm getting constructive interference because my lines keep on lining up. And in between, I get areas where crests line up with troughs, and troughs line up with crests, and so on. So I get constructive interference, and then on either side, destructive, constructive, destructive, and so on. Notice, for example, that there's no way light could just go straight through and then hit the screen in the middle, and yet I get a bright spot here. So that could only happen if this was exhibiting wave-like behavior, if it was bending around the corner. And so this experiment shows very clearly that light, at least sometimes, can act like a wave, okay? So we take a single coherent source of light, same wavelength, pass it through 2 small slits and project on a screen. The resulting pattern shows a maxima and minima, maxima being the bright spot. When 2 crests meet, we see constructive interference and a maxima. 2 crests or 2 troughs. When a crest meets a trough, we see destructive interference and a minima. So you're going to see a dark spot. Okay. So let's try and just break this down. Let's just try and understand mathematically kind of how this happens, where this comes from. Okay. So I'm going to draw just a single step in this, and I need you to keep in mind that this is a repeating pattern that happens over and over again. And I'm just going to draw just the first maxima and kind of try and think about how that goes. So you're going to need a ruler for this next part because we want to get this at least approximately correct. So I've got a screen over here. Here's my screen. And I've got my double slit on this side right here. And the first thing I want to just define is that the distance between the slits is going, I'll just call that D. Okay. Now, the distance to the screen, which we'll just do like a dotted line here. Okay, dotted line. I'm going to call that distance L. Okay, that's my distance to the screen. And notice that we have our first maxima, our brightest bright spot happens right here. Now, we're going to call this maxima M equal 0 for kind of our central maxima, I should say. Now, both above and below, the same distance away, I'm going to have another maxima. And I'm going to call this M equal to 1. I have another maxima down here. Okay, I'll call this M equal to 1. You can call it -1 to distinguish. It doesn't matter. The point is that they're both the same distance from the central maxima. So I'm just going to focus on this top maxima here, and I'm just going to draw like a line that connects kind of from here to the center of my double slits. Okay, and you can see that I've got a distance. So how far is the central maxima to this first maxima here? I'm going to call that X. Okay, sometimes they call it Y. Again, doesn't matter too much. Okay, so let's think about this. Well, first thing to notice is that that the reason I got that maxima was because light traveled from these two slits and struck that point. So again, I'm going to draw these in different colors, but they are not different colors of light. This only works if it is the same color of light, obviously going through each maxima. So I'm going to kind of draw a line from here right to the center of that slit there, to the center. Okay. And then I'm going to draw another line here to the center of the upper slit. Okay, like that. Very nice. Okay. Now, a few things that we have to point out here. In reality, for this to work, L is going to be much bigger than X. Okay, so the way I've drawn it kind of looks like, oh yeah, L and X, they're like sort of reasonably similar size, but they're not. I would need to like project this on a screen like several meters away, and then I might notice a separation of X in the order of millimeters, depending on the wavelength of wave that I'm using and so on. But just for the purposes of this drawing, I've kind of compacted it a little bit so that we can see it a little bit better. But so why do I get a maximum? Why do I get a maximum at that point? Well, the reason I get a maximum must be because I'm getting constructive interference. And that means that the crests that are coming from this like red line, let's say, following that red line, and crests that are following the blue line must arrive at that same point at the same time and interfere. And that makes sense, except it's pretty clear that the waves that follow the red line travel a shorter distance than the waves that follow the blue line, right? If I connect these with a line like this, and I connect them like this, you can see that pretty clearly the blue line is longer. So how is it that I'm getting constructive interference? Well, the key here is that what needs to happen is I need crests to arrive at the same point at the same time. It doesn't matter how far they've traveled. So this blue wave here is traveling a little bit further. I'm going to call that delta L. And the amount that it has to travel further in this case is equal to exactly one wavelength. You can imagine that if the waves that follow the blue line travel exactly one wavelength more than the waves that follow the red line, well then crests are going to arrive at the same time as crests, and so will troughs. Now, this is the first maxima, so this pattern repeats 2, 3, 4, 5, and so on. So I'm just going to put an M here to represent any integer being the number of wavelengths that it travels in addition. You can imagine if we reverse this picture and looked at the maxima down here, then it would just be the red waves, or the waves following the red line would travel a little bit further, but again, it would be by the exact same amount. So the first kind of thing to make a note of here is the difference in length between what the waves travel is just some integer number of wavelengths, okay? And so this M refers to my maxima, and it has to be an integer. Okay, so we're going to look at the geometry of this a little bit, and it is going to get a little bit funky. Notice that there's an angle here in that little small triangle. That angle would equal this angle right here. And I'm not going to prove it geometrically. I'll leave that to you to kind of wrestle with, but in fact, those are true. Now, the other thing to recognize is that this distance here, L, the distance to the screen, is not the exact same as the length of this red line, but they are very, very, very close, because remember, that screen has to be a long, long distance away just to get a separation of a few millimeters. So while it looks like I'm going to break a few rules here, they are very, very good approximations. So first thing to notice here is that if I look at this triangle, that if I take the sine of theta, when I look at this small triangle, that is going to equal m lambda over d. So I can rewrite this formula here, and I'll just put this over the side here, that d sine theta is equal to m lambda. Okay, so if I want to know the angle between them or whatever, or I want to kind of figure out the distance in the slits, I can do that with that formula. But let's take this a step further. Let's now look at this, let's look at this triangle here, the kind of the dotted triangle. Well, I could take the tan of theta, and tan of theta is going to equal x over L. Okay, so I've got another kind of formula. And this is kind of the weird part. Because theta is very, very small, and this only works because theta is very, very small, we can use the small angle approximation. So since theta is very small, then the sine of theta actually equals, or is approximately equal to the tan of theta. So I can set these two things equal to each other and solve for x, and say x equals m lambda L over d. And so this gives you an idea of how you might calculate your distance for your interference pattern. Okay, so let's take a look now at single slit interference. And single slit interference is actually a little bit trickier to understand in some ways, which is why we start with double. But just recognize that when you shine light through a single slit, you actually kind of somewhat surprisingly get, again, an interference pattern. You might wonder, why don't we just get a bright spot in the middle that just gets continuously dimmer if the waves are just going to propagate out as they bend through that new space once they go through the opening? And the answer is that in addition to the waves bending when they go through the opening, each corner actually acts as a new point source for waves. So as that wave goes through and bends, in addition, I get a new kind of wave propagating out from each of the corners. And I'm not going to try and draw this because it's going to go terribly, but just recognize that while the wave that hits the middle is very much the brightest, you can see how large the central maxima is. We are going to get this repeating interference pattern as we move outwards because of the waves on the corners that are going to interfere with the waves that kind of go straight through. So we're going to get a situation where I get I'm going to get a central maximum here, okay, like we saw, and we call that m equal to 0. Okay, so I get my central maxima, which is m equal to 0, and I'm going to call that is a maxima. Okay, and I will get another maxima up here somewhere. Okay, here's another maxima. But in the middle, between these two, I'm going to get a minima. And I'm actually going to call this m equals 1. And that seems weird based on what we just learned, but I'll explain why here. Okay, so waves travel through and strike the center of the screen. So I'm going to draw a line from the center of my opening right through and hit the screen. And we'll use the same terminology we used before. So for example, we could call this x, and we can call this distance here d. Now d refers to the width of the opening as opposed to the distance between the two slits. Okay, so I'm going to draw a line here from my minima to the corner of the opening right there, right? Because that's where my other light source is. That's the other source that it's coming from. And so what I'm trying to understand is, why is this formula here, x equals m lambda L over d, why does this formula work for both single and double slits? Now, of course, with the double slit, this predicted the location of the first maxima. And then for single slits, it predicts the location of the first minima, like what's going on there. So recognize that there's a path differential here. That light that travels from the center of the slit to the minima is going to travel a different distance than light that travels from the edge of the slit. Okay, so we get the same kind of situation happening where I've got a path difference, okay, and I've got a little angle theta there that's very hard to see, and this little point right there would be my difference in path, which is m lambda, so that's all still the same. And then I've still got an angle here, which is correspondent to that angle there, and then that angle there, and so on. But again, why does this formula give me the minimum? But the reason this formula works is because take a look at what x is actually telling us. X is telling us the distance from the central maximum to the first minimum, which is halfway to the first maximum. And then notice over here that when I call the distance the size of the gap, the size of the opening d, in actual fact, I'm actually only looking at 1/2 of d when I draw this diagram. So the end result is this formula ends up predicting where my first minima is, not my first maxima. We need to take a look at one last thing, which is thin film interference. Now, this is one of my favorite things in physics because it helps me explain why bubbles have rainbows in them, which is great. So if you look at a bubble, a film that's on a little bubble blower, before you blow the bubble, you might notice that there are rainbow patterns, and not just one rainbow pattern, but like a repeating rainbow pattern. Now, slightly less majestic, but no less physicsy is if you see an oil slick on the ground. Now, oil on asphalt doesn't look like much, but after it rains, when the oil floats to the top of the water, we see these rainbow patterns. Now, notice that not only do we see all the colors of the rainbow, but they become regular. So they're like concentric, or in this case, like it keeps reoccurring. It goes red, yellow, blue, green, orange, indigo, violet, and then over again, over and over. So let's try and understand why that happens, okay? In both cases, this happens because of something called thin film interference. Thin film interference. And you can appreciate that like a bubble, like before you blow the bubble sitting on the bubble blower, is a very thin film, and that the layer of oil sitting on water on the ground is a very thin film. And so these things only happen obviously when we talk about thin films. So what is going to happen when light strikes these objects? Okay, well, whenever light reaches a new medium, we know three things happen. But in particular, because this is reasonably translucent, we're going to have some of the light is going to reflect and other light rays will refract. Okay, so some light will bounce off, some light will go through. Great. So what happens next? Well, the refracted rays that go through are then going to reach another barrier. In the case of the bubble, it's going to go from air into bubble into air. And in the case of the oil slick, it's going to go from air into oil into water. And so it's going to reach a new medium on the other side, which means, again, some light rays will reflect and other light rays will refract and travel into the new medium. Well, those reflected rays, both the ones from the first surface and the second, are going to end up in the same point again. And so if those light rays interfere, if they're in phase, they will interfere constructively. And if they're out of phase, they'll interfere destructively. Now, of course, keep in mind that different colors of light are just associated with different wavelengths. So there must be something about this film where it is causing certain wavelengths to constructively interfere and others to cancel out. So when you see red in the bubble, that's a region of the bubble for some reason that's showing you a lot of red, but not really showing you a lot of the other colors. And when you see purple, exactly the same thing, but for purple. So let's just jump down to a diagram here and try and make sense of this. Now, I want to point out that this diagram also is a little bit shifted just so that we can understand it, and that the light rays don't need to come in at an angle like this and bounce off, but we're just going to use this diagram because it's going to be easier for us to understand. The light rays might travel straight down and bounce virtually straight back for all we know. Now let's use the example of the oil slick in this example. So what we have is we have light coming in, and this incident light is going from air into oil and then eventually into water. Okay, and then of course, like at the bottom here is like asphalt. Now, light that hits asphalt is going to mostly absorb, so we can kind of just ignore what happens after that point. So light comes in, and let's keep in mind what happens here. So light is going to come along. You can see it's going to follow this ray here, and some of it is going to reflect, and some of it is going to refract. But the stuff that refracts into the oil, again, some of it is going to reflect and some of it will refract again, but I'm not super interested in that stuff because it's going to get absorbed by the asphalt. You see that the ray that reflects, number one, and the ray that refracts and then reflects, ray number two, could strike the observer who's standing watching this all happen. Now, if those two rays interfere constructively, then you're going to see that color. And if they interfere destructively, you're not going to see that color. Now, what does that all depend on? Well, notice that I've got a certain thickness of the film. It's going to depend on the thickness of this film. The thicker the film, the thinner the film, that's going to change what color you see. Now, why is that? Well, let's think about what happens with the light rays when they strike this new surface. So the first thing to recognize is that light is going to have a certain phase. And so I'm just going to use the symbol phi for phase. And I'm going to say that the original light ray is at 0 degrees of phase. It has not been shifted at all. So the incoming light all is in the same phase with itself because of course it is, okay? And I'm going to use degrees, not radians. I'm sorry. What happens when it reflects? Well, the light ray that reflects, remember, if you bounce off a higher density material, then you are going to go through a phase change. So this is going to have a phase change of 180 degrees. Now, what about the light that refracts in? Well, this light that refracts in, when you refract, you don't change your phase. So this is still at 0 degrees. This is still in phase with the original light that was incoming. But when it bounces off the water at the bottom here, that is going to be a higher optical density. So this is going to undergo a phase change. And so when it bounces off, we have another shift. And then we go through and we refract when we get to the surface. And so this is going to be at the original 180, or the phase shift that it had, the same as before. So both of these reflected waves have been phase shifted by 180 degrees, which means they are in phase, except this wave that went through, ray number 2, had to travel through the oil and back again. And so this distance is important. What would it take for that ray number 2 to be perfectly in phase and aligned with ray number 1? It's traveled a greater distance, but you can imagine that if the distance it travels there and then back was equal to exactly one wavelength, well, then we would see those waves line up again. So distance there and back is one wavelength, which means the distance d would equal lambda over 2. If the distance, the thickness of the film is equal to exactly one wavelength, then the waves that go through and bounce back will line up perfectly. And so this is what we see here in our bubbles or in our oil slick. And an area right here that's quite blue, that is just the right thickness so that blue light that travels through and back is going to be perfectly in phase with light that bounces off the surface, and it's going to look blue because the other colors of light will be at least somewhat destructively interfered with, whereas blue is going to be constructive. And you can see this film must be slightly different thicknesses in different areas, which is as you go from blue to green to yellow to red, we're just changing the thickness of the film, which corresponds to a different color of light. Now think back to this pattern here, or the oil slick. This pattern was repeating. We went from red to blue, or we went from red, orange, yellow, green, indigo, violet, and then back to red again. Well, why is that? So these thicknesses must correspond to different possible ways. It's possible that the film's getting thick and then thin and then thick and then thin, but that's not very likely at all. In actual fact, what it means is we don't have to travel exactly one wave in that film. We need to travel some integer number of waves when we're in the film. So actually this formula that we come up with here is correct, except we need to add a little m, where again, m is just some integer. Okay, well, not like any integer like a bajillion, but like some small integer. And so that's why we get this repeating pattern here. So the film will have different thicknesses at different points. And so the thickness of the film is related to the wavelength. And since it's related to the wavelength and therefore the frequency, that means it's related to its color. And it tells you which wavelength of light you're going to constructively interfere with. Okay, that is it for diffraction and interference.